Hi guys, welcome to another lecture in the series General Inorganic Chemistry. And today we're going to do the first part of chemical bonding. Alright, so I'm pretty sure that you might be familiar with the types of chemical bonds. So, let's just do a review. So whenever two atoms or ions are strongly held together, we say that they're in a chemical bond, right? And you are familiar, I'm sure, with these three general types of chemical bonds: your ionic, your covalent bond, as well as your metallic bonds. So, continuing this review, the ionic bond, and the most popular perhaps bond that you might know of is your table salt, right? And so it's sodium chloride NaCl, and it consists of sodium ions. So sodium is positively charged, and chloride ions, which has chlorine, which is negatively charged, right? So the distinction here between chlorine when it's not charged as opposed to when it is charged, when it has accepted an electron and is now chloride and it's now an ion, right? So it's held together due to the electrostatic attractions between these oppositely charged ions. So that is, in this case, the sodium positively charged sodium ion, the negatively charged chloride ions. So here, on this image to the left, we see or example or a diagram or a picture of sodium chloride, right? And that is our ionic bonding held together via electrostatic attraction. And the sodium chloride will look somewhat like a cube with alternate positive and negative charges. Now, for our covalent bond, the most common molecule that might come to mind is water, right? So we say that it's a consists of covalent bond or covalent bonds, since we have two. The hydrogen and oxygen atoms are bonded to one another through covalent bonds, as we said, in which molecules are formed by sharing of electrons. So ionic, there's no sharing, there's transfer of electrons, right here. Transfer of electrons, so we get a positive charge and a negative charge. Here with covalent bond, we're saying there's a sharing of electrons. And here we have an example of the water molecule with electrons shared, right? So we have our two hydrogens and we have our oxygen, and we have sharing between both the hydrogen and the oxygen here, and the hydrogen and the oxygen here. And then finally, with regards to our types of chemical bonds, we're looking at the metallic bond, right? And here our example is the stainless steel spoon, which consists of, generally there are other elements, but we're saying here that it consists mainly of iron metal, in which the iron atoms are connected to one another via metallic bonds, which are formed by electrons that are relatively free to move through the metal, right? So here we have an example of metallic bonding. So this is here, electrons are delocalized, and clearly that's the opposite of localized, being in one position. Delocalized mean that it's spread all over. And because of that, you have the negatively charged electrons moving around. That gives rise to metallic bonding. So these different substances that we see in the image here, or stainless steel spoon, or sodium chloride, and or water in the glass, right? They behave as they do because of the ways in which their constituent atoms are connected to one another, right? that is ionic covalent metallic. So, for example, sodium chloride, as we know, it readily dissolves in water. But if we put our spoon in the water, we're pretty sure that it will not dissolve. And that has to do with the nature of these chemical bonds. All right, so the next thing that we want to look at is Lewis symbols and the octet rule. And so the electrons involved in chemical bonding are actually called the valence electrons. So these are the outermost occupied shell. And the American chemist G.N. Lewis suggested a simple way of showing the valence electrons in an atom. So when you see it, and we'll see it in the slide coming up after this, the only thing that we're seeing are the valence electrons. So yes, we know that the atom has other electrons, but Lewis said, let's just focus on the valence electrons for a little bit so that we can understand the nature of these chemical bonds. And so we can track them during the bond formation. And so now it is known as the Lewis electron dot symbols, or just Lewis symbols. And here is an example of the Lewis symbol for sulfur. So the Lewis symbol for an element consists of the element's chemical symbol plus a dot for each valence electron, right? So we have our symbol for sulfur, which is capital S, and when we have a dot for the valence electrons, so that represents the valence electrons. So for sulfur, for example, we say that it has an electronic configuration of, and we can say 1s2, 2s2, 2p6, 3s2, 3p4, right? So that will be the extended or the expanded electronic configuration. And so clearly our electrons, our valence electrons, are in the principal quantum number 3 shell, right? And so we count 4 plus 2, 6 valence electrons. And so for the Lewis symbol, we have, of course, the chemical symbol and a dot for each valence electron, right? So 2, 4, 5, and 6. So the dots are placed on the 4 sides of the symbol. So we have the top, the bottom, the left, and the right. And each side can accommodate a maximum of 2 electrons, right? So you won't see more than 2 at either the top, the bottom, the left, or the right. All 4 sides are equivalent, which means that the choice on which sides to place 2 electrons rather than 1 electron is arbitrary, right? So we could draw it like this as well, right? So we could draw it like this, we could draw it like this. They're all equivalent. So in general, we spread out the dots as much as possible. And so in the Lewis symbol for sulfur, for instance, we prefer the dot arrangement shown here rather than this one. And rather than the arrangement having 2 electrons on 3 of the sides and none on the 4th, which is this one, right? So it's more spread out, and that is the preferred way of writing the electronic configuration, the Lewis structure for sulfur. So first question, are all these Lewis symbols for chlorine correct? So take a second and look at it, maybe pause the video and before we look at the answer to that, right? So what we want to look at here is firstly want to check the number of valence electrons, if that is correct, and then how they are distributed, if that is correct as well, right? So we want to count. Here we count 7. We count 7 here, and we count 1, 2, 3, 4, 5 here. So the first thing is that correct? Is it 7 or 5, right? And then the second thing we want to look at is the distribution. So we don't have more than 2 electrons at any one, whether top, bottom, right, or left, right? So I'm sure you got this correct. This one would be the accurate one because we know that chlorine is in group 7 and therefore it has 7 valence electrons and not 5. So here we have the Lewis symbols for a few elements seen here, right? So we have the group, the element, the electronic configuration, and the Lewis symbol, right? So for lithium here, we see that the electronic configuration or the valence electron is in the 2s subshell, and so and there's just one electron, and so this is the Lewis symbol. And so, I mean, perhaps you want to take a minute and just go through all of them just to see their Lewis structure. So we just saw chlorine in the questions, in the previous question, and this is the Lewis symbol as we saw. And we also saw sulfur when we were introducing the topic, right? So just take a second and go through and ensure that you understand the relationship between the group, right? So notice that there's a correlation between the group number and the number of valence electrons, right? And also look at how we place the dots on the Lewis symbol. So take a second and make those connections. So atoms often gain, lose, or share electrons to achieve the same number of electrons in the noble gas closest to them in the periodic table. So let's look back at sodium chloride. When we're talking about ionic bonding, right? So here, the sodium would have lost an electron and the chloride would have gained an electron, right? And that is how we have a ionic bond. For a covalent bond, we know that the electrons are shared as we saw in water, right? So this is what we're looking at. Electrons are either lost or gained or shared to achieve the same number of electrons as the noble gas closest to them in the periodic table. And that's because the noble gases are very stable. They have a very stable electronic arrangement, evidenced by their high ionization energies, low affinity for additional electrons, and just general lack of reactivity, as we have seen. And this is so because all of these noble gases except helium has 8 valence electrons. Many atoms undergoing reactions end up with 8 valence electrons. And because scientists have seen this pattern over and over again, it has led to the guideline known as the octet rule, right? And that means that atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. So there's a method to this, apparently. So let's look at the ionic bonding that we mentioned earlier. So these substances generally result from the interaction of metals on the left, as we saw with sodium, and non-metals on the right side of the periodic table. And of course, we're excluding the noble gases because we just mentioned that they have low reactivity based on the fact that they are very stable. So for example, when sodium metal is brought into contact with chlorine gas, a violent reaction ensues. And so the product of this very exothermic reaction is sodium chloride, right? So this is the synthesis of sodium chloride. So we have this solid that is a metal, and we have this chlorine, which is a non-metal on the right side of the periodic table. When they fuse, and it's a gas, of course, right? So when they fuse solid and gas, we get sodium chloride, right? So it's an exothermic reaction, which is why we have the enthalpy of formation being a negative value. And that means, of course, that energy is lost. So here we see a diagram that kind of represents the reaction. So we have the chlorine, and it's a gas, so it has to be in a sealed container, right? And then we have the sodium, which is a solid. So, I mean, clearly this would be under controlled conditions, because if you open a lid with a gas, it will escape, right? And so, just for explaining purposes, we're saying that we drop the solid inside the container, close it back. So in the container, we have chlorine gas and the sodium, which is a solid, right? And when they react together, it's an exothermic, a highly exothermic reaction, and it forms, notice there is the white solid here at the bottom, which is now an ionic compound composed of sodium ions and chloride ions, of course, right? So what happens here is that we have an electron transfer. The electron leaves sodium, and the chlorine actually gets that electron, and that is how it becomes negatively charged and therefore a chloride ion. And of course, this is the equation for that reaction. So the formation of the sodium ion from sodium and the chloride ion from chlorine indicates that an electron has been lost by a sodium atom and gained by a chlorine atom. And so the electron is lost by a sodium atom and gained by a chlorine atom, as we said. So there has been an electron transfer from the sodium to the chlorine atom, as we see demonstrated here. So notice that we're seeing the Lewis structure because sodium has only one valence electron. And so that electron now is transferred to chlorine, which has 7 valence electron. And once it gains that electron from sodium, it now becomes negatively charged. And we have sodium here that is positively charged because it lost an electron. All right, so continuing here with our ionic bonding, the two atomic properties give us an indication of how readily electron transfer will occur. So what we want to look at is the element's ionization energy, which tells us how easily that electron, so for example, sodium, we know that it loses an electron, right? As we just saw. So we want to know how easily will that happen, and the ionization energy will give us that data or information. For the electron affinity, we want to know how much an atom like chlorine wants to gain an electron, and our electron affinity will give us that information. So electron transfer to form oppositely charged ions, that is positive and negative, occurs when one atom readily gives up an electron, and therefore it has to have a low ionization energy, and the other atom needs to have a high electron affinity, meaning it wants to gain electrons, right? And so for our typical sodium chloride, which is an ionic compound, a typical ionic compound such as sodium chloride, It consists of a metal of low ionization energy, which is sodium, and a non-metal of high electron affinity, which is chlorine. So using the Lewis electron dot symbols and showing the chlorine atom rather than the chlorine molecule, we can represent this reaction as seen here below, right? So just a point to note here that what the species that actually reacts with sodium is the gas, which is diatomic, right? But we're just showing here for the purposes of explaining ionic bonding, we're just seeing the elemental chlorine and not the molecular chlorine, right? And so it will gain an electron and therefore become negatively charged, and of course the sodium, as we mentioned, can lose an electron and so become positively charged. So what are the properties of some ionic substances? Well, they are usually brittle substances with high melting points. They're usually crystalline. The ionic crystals often can be cleaved, that is, they break apart along smooth, flat surfaces. These characteristics result from electrostatic forces that maintain the ions in a rigid, well-defined 3D arrangement, as we saw with sodium chloride. So next question. Describe the electron transfers that occurs in the formation of calcium fluoride with elemental calcium and elemental fluorine. So take a second and attempt this question. So what happens in this electron transfer between calcium and fluorine? All right, so if this is what you had, then congratulations, you are correct. So we have the dot and cross diagrams here, and our cross represents the valence electrons for calcium, and our dots represent the valence electron for fluorine. So we have two fluorine atoms, right? Because the fluorine is a diatomic gas, right? And so here we see that one electron will be lost to one fluorine and the other electron will be lost to another fluorine, right? As we see here. So one electron will go here, one electron will go here. So we're not sharing electron, we're transferring electron. And because the calcium lost two electrons, it is now calcium 2 plus, and each fluorine would have gained an electron and so become fluoride ion, right? And which is negatively charged. So two of them would be negatively charged, right? So we have two ways of writing it and essentially end up with the same thing for calcium fluoride. So for covalent bonding, Lewis reasoned that atoms might acquire a noble gas electron configuration by sharing electrons with other atoms, as we saw, right? And so a chemical bond formed by sharing a pair of electrons is called a covalent bond. So just another review, because we saw that already. So the formation of covalent bond can actually be represented by Lewis symbols, right? And so for hydrogen, where we have two hydrogen atoms, can be represented as seen here. And in forming the covalent bond, each hydrogen atom requires a second electron, right, to achieve that stable noble gas helium configuration, which is 2 electrons. For the Lewis structures for these covalent bonds, and so let's look at that. So the structure shown here for hydrogen and chlorine are Lewis structures or Lewis dot structures. So while these structures show circles previously to indicate electron sharing, the more common convention is to show each shared electron pair as a line, and any unshared electron pairs, or unshared electron pairs, as we see here around the chlorine, they can be called lone pairs, as well as they can be called non-bonding pairs, right? And it's written in this way. So the line itself for the covalent bond represents the shared electron pair. So just a reminder here that for nonmetals, the number of valent electrons in a neutral atom is the same as the group number, right? So we want to look at the group number for our metals or nonmetals and look at how they correlate with the number of valence electrons. So we might predict here that the group 17 elements, or 7, notice here that we go between 17 or 7, such as fluorine, would form one covalent bond to achieve an octet, right? And so from group 16 or 6, such as oxygen, would form 2 covalent bonds, and for nitrogen, which is in group 5 or 15, would form 3 covalent bonds in order to reach that octet. And for carbon, for example, which is in group 4 or 14, we would need 4 covalent bonds to satisfy the octet. Alright, so what I would love if you would do you would literally just count the electrons just to ensure that we have an octet, right? So notice here that the line represents the shared electrons. That would be 2 electrons, so 2, 4, 6, 8. And here the line represents the shared electrons, so it'd be 2, 4, 6, 8. Again, 2, 4, 6, 8, and here 2, 4, 6, 8, right? So at the end of the day, for fluorine, which is in group 7 or 17, we want 1 covalent bond to achieve our octet. For oxygen, we need 2 covalent bonds to achieve our octet. For nitrogen, we need 3 covalent bonds to achieve our octet. And for carbon, we need 1, 2, 3, 4 covalent bonds to achieve our octet. So here, we're basically saying the same thing in a tabular format, right? So we have our nonmetals here. We have the group number, and we have the number of valence electrons, so 7, 6, 5, 4. And we also have the number of covalent bonds that is required to reach our octet. So notice here that once we add these numbers together, we get 8. So 7 and 1, 8. 6 and 2 is what? Yes, 8. 5 and 3 is 8. And 4 and 4, 8 as well, right? So this is a nice little table to remember that. All right, so question: predict the formula of the stable binary compound. And binary compound means a compound composed of 2 elements formed when nitrogen reacts with fluorine and draw its Lewis structure. So take a second and attempt that question. Alright, so if you drew this, then you're onto something, right? So we have our nitrogen, and based on our table, right? For nitrogen, we need 3 covalent bonds in order to reach our octet, right? So here we have 3 covalent bonds that nitrogen used to achieve its octet, right? And so clearly our line represents our covalent bonds, and we have our other valence electrons, which we call unshared electrons or non-bonding electrons, right? And of course, lone pairs. So we can call them unshared electron pairs, lone pairs, or non-bonding pairs. All right, so far we have only seen single bonds, but what about multiple bonds? So a shared electron pair consists of a single covalent bond, generally referred to as a single bond. So in many molecules, atoms attain complete octets by sharing more than one pair of electrons, and that is how we end up with multiple bonds. So when 2 electron pairs are shared by 2 atoms, 2 lines are drawn in the Lewis structure representing a double bond, as we see here. Right, so we have carbon here that has 4 valence electron, and here we can show the sharing of this electron and this electron and this one and this one to form the double bond on this side, and then this and this and this and this to form the double bond on the other side, right? So at the end of the day, we end up with 4 pairs, 1, 2, 3, 4. That's our 4 lone pairs or non-bonding pairs or unshared electron pairs, and we end up with 2 double bonds to form carbon dioxide. And of course, you have triple bonds, right? So for example, in nitrogen gas or molecule, we have, this is the Lewis structure for nitrogen, right? So we can have these 2 electrons being shared with each other. These 2 can be shared, and these 2 can also be shared. And so if we have 3 pairs, then that means we have 3 bonds, right? And 1 lone pair left. So this is the Lewis structure for nitrogen. All right, so just to wrap up this lecture, I want to just end with just mentioning bond polarity, and of course we're going to pick up from here in the next lecture. So bond polarity and electronegativity. So bond polarity is a measure of how equally or unequally the electrons in any covalent bond are shared, right? And so a nonpolar covalent bond is one in which the electrons are shared equally, as in Cl2, which is chlorine gas, or nitrogen, as we just saw, nitrogen gas, right? Which are both diatomic molecules. In a polar covalent bond, one of the atoms exerts a greater attraction for the bonding electrons than the other, right? And so if the difference in relative ability to attract electrons is large enough, that's how we get an ionic bond, right? So we're going to go a little bit more into this, but the idea here is that when you have 2 elements bonded together, we have to look at how they relate to each other. Is one atom pulling electrons to itself more than the other? And if so, then we have a polar bond. But this bond can be, polar covalent, meaning they're still sharing, the one element is pulling to the other side, but it's still being shared. And if that difference in electronegativity is large enough, then that's how we get an ionic bond. So the element will literally pull the electrons fully to itself, and that's how we get an ionic bond. All right, so let's pick up from here in the next lecture. And so that's all for now. Thank you so much for watching.